Good afternoon. Am I audible?
Yes, sir. Good afternoon. And you are audible.
Okay. So can you see the screen right
Yes, sir.
now? Okay. All right. Computational science students, is anyone there? Anyone from computational science is there?
I think no one, sir.
Okay. So yeah, so they can attend the class. So we have got the written permission now. So that is what I wanted to share. So okay, I will write on the WhatsApp group.
Due to all 7 colors we have with the
Okay, so
with these
last class we
particles.
have seen basically we have completed photodiodes. So actually, today actually what I will try to do is I will just change the nomenclature a little bit. Time what we were calling photodiodes, actually we can use photodiode word as a more generic term so as to include both solar cells as well as photo detectors. So what we studied like class only as photodiodes, actually we are mainly talking about photo detectors. So those which are used to detect level of light intensity. So it basically converts your light into electrical energy, but that is used to uh, detect light, not in the sense to get energy from it, like we use solar cells. So you remember that we have seen that the solar cell is used in the fourth quadrant where voltage is positive, that is forward biased, and your current is in the reverse direction. So overall the power is comes out to be negative, and so you can actually extract power from the solar cell. And when we use this PN junction in the reverse bias, and there is a reverse current because of this illumination or light which is shining on it. So that is known as is basically the use of the PN junction as a photodetector. So when you use it in a third quadrant with both current and voltage negative, you are actually getting positive power, which means you need to send power into the device. But what it is then doing is it is actually um, giving you a current which is proportional to the level of light which is falling on this photodetector. So that is why you can use it as a photodetector. Means you can convert the light. You can have a understanding of what is the level of this light which is falling on your photodetector. So that is what. So we were talking about this photodetector as a photodiode last class, but photodiode you can consider both solar cells as well as photodetectors as photodiodes. Means diodes which have something to do with light. So solar cells convert it into energy, whereas photodetectors are used to.
Hello, sir.
Yeah.
Sometime your voice is breaking, sir. Once again, tell me, sir, what you were last 1 minute explaining.
Okay. All right. Okay. Some people are still joining.
Okay, sir.
No, it's fine. Just I have to keep on adding them from time to time in the middle. So people should join in the very beginning, right? You should not join late. Okay. So yeah. So um, So right, what I was saying was that photodetectors are used in the third quadrant and solar cells are used in the fourth quadrant, right? So in the third quadrant, as you know, the power is being used by the device, whereas in the fourth quadrant, power is being generated by the device. So then it's a solar cell. So both this photodetector and solar cells are examples of photodiodes. So photodiode is the generic name which you can apply to both solar cells as well as photodetectors. So is that clear now, what I
Yes, sir. Yes, sir. Yes.
said? Okay. Okay, so that is what I'm saying. Last class, I actually called photodetectors as photodiodes, but I'm now increasing this the scope of photodiodes to include solar cells also, and specifically the photodiodes which we saw last class, I'm calling them as photodetectors. So that is what I was trying to tell actually. Okay, so that is what we have written. I've written here means we can call photodetectors and yeah, so we can call photodetectors and solar cells both as photodiodes, and the solar cell is operated in the fourth quadrant because its power is negative, while the photodetectors and are photodiodes which are operated in the third quadrant where both current and voltage are negative. So this is what I'm illustrated again. So you can see that there are four quadrants of the I and V, and in the third quadrant where both current as well as voltage are both negative, there you get photodetectors, and if you use it in the fourth quadrant, you get solar cells. And this green curve is the normal diode characteristic, right? So you know the diode characteristic passes through the zero, that's the origin. When both forward and bias is zero, then there is no net current flowing through this device. So the green curve you can see is flowing through the origin, and it rises very sharply after that. So after the knee voltage, which is like 0.7 volts for silicon, the green curve shoots up very rapidly. And you know that that equation is this. So this is the diode equation which I had told you about. Okay, so now what you can do is, now when this, when you reverse bias it, then there is a reverse saturation current, which does not depend upon the applied voltage. So the green curve you can see is almost flat, and that is actually in few 100 nanoamperes. So that is the reverse saturation current. And if you go beyond certain level, like the Zener breakdown voltage, which might be somewhere here, if you go beyond it, then you know that the curve will suddenly shoot up. So that is your that would be your reverse breakdown or Zener breakdown.
Sorry, your screen is not with. Yes, sir.
Yeah. Sorry? Yeah, can you hear me now?
Yes, sir. Yes, sir.
Yeah, so I said this green curve is the normal diode, right? So that is the normal diode equation which you get from here. Now, if you shine light on this reverse biased PN junction, and then what will happen is this light will fall in, say, the depletion region. It will generate electron hole pairs, right? And this electron hole pairs the minority electrons and the minority holes. So the electrons which are there in the which are generated, say, in the p-type region, and the holes which are generated in the n-type region, they can easily flow from to the other side across the junction. So that will lead to a reverse current. So this current will be against the normal forward direction of the current flow in a diode, and hence this is like a reverse current. Now, when there is no light, then this is the level of current you get as shown in this green curve. If you shine some light on it, then you will get this, say, the purple curve here. So you can see now that it does not pass through zero anymore. That is, it does not pass through origin anymore. So this is, for example, this is your short circuit current, if you remember from the solar cell, and this voltage will be your the open circuit voltage for that solar cell, for that intensity of light. And now we are concentrating on the photodetector part, that is we are in the reverse biased region, in the third quadrant region. And now again, if we increase the light, suppose IL2 is the new level of light intensity, and suppose it is just twice IL1. So you can see what happens is the current also almost doubles. So whatever the current value was here, you can see it's roughly doubled when you shine light intensity twice the initial light, and so you get this orange curve. Again, you can see that this will be the short circuit current, and the voltage, the voltage, the open circuit voltage more or less remains the same. So you remember that we saw that intensity in the solar cell, if you increase, the current increases, but that does not happen with the case of the voltage. So the voltage kind of becomes saturated, becomes constant after some intensity of light. So like that, if you again increase the light, and you will again get a higher current. And so that is how your photodetector works. Why photodetector works is because the current is linearly increasing as you increase the level of light. So when you want to detect something, you want some proportionality, right? So suppose you want to, here you're detecting light, so you want something which will increase as you increase the light. So that is what is happening. So as your light level goes up, your current, your reverse current is also going up, right? So that is the basic concept of photodetectors.
Sir,
Yeah.
sir, here dark current means what does that mean, sir?
Yeah, so dark current means when you have not shown any light. So when there is no light shining on the PN junction.
It means normal temperature.
So temperature is always same for all these curves. So suppose it is 25 degrees Celsius. So it is the same, 298 Kelvin for all. So temperature is not changing, but what is changing is the intensity of light. So this is your PN junction. This is say reverse biased. So this light which is falling on this, that is changing. So if there is no light, suppose no light, then this is green curve, that is dark current. So that is the reverse saturation current in a normal PN junction when there is no light. And when
we will consider it's like a night time.
It's like just a dark room, and there you have a PN junction which is reverse bias, right? You can consider like that.
Dark room means no light. It means night time. Yes, sir.
Yeah. So there is no light falling on your, or you have covered your diode and there is no light falling on it. It's not necessary that you can only do night.
So in daytime, compulsory light will be falling, na?
Yeah, but if you enclose it in some thing, then there might not be any light, right? If you encapsulate your a diode in something, then there will be no light.
Okay, sir. Okay, sir.
Okay.
Sir, one more case here. We are in photodetector. It will be power consumption we are using. Power consumption means what we say?
So you are supplying power to the photodetector. It's only power consumption means what?
Sir, here we are incident only intensity, na? But
So you have joined your diode in this manner, right? So this is P, this is N. So this is reverse biased, okay? And there is a reverse current. So normally current flows from P to N, so the current is flowing in this direction. So what is happening is you are sending current like this. So the power is being dissipated in this device, in this PN junction. So your PN junction is not giving you power. It is consuming power, but its role now is not to generate power. Its role is to just convert light to electric signal, which is proportional to the level of light intensity.
Sir, it means we are giving external bias. Yes, sir?
Exactly.
Okay, sir. Okay, sir.
Not only you're giving not only a bias, but it's also consuming power. Whereas in a solar cell, actually, you are getting power from the solar cell. Okay.
Okay, sir.
Okay, so Right. So that is what I have written here, what I've just explained to you. And you can see, so the same graph which I had shown in the last curve can be, from that you can actually generate this curve. So what this curve is, it is at a fixed voltage. So see, the voltage is 20 volts. So the reverse bias is 20 volts, and what you're plotting is your so it depends. This I naught, not the expression for that. It depends upon the doping and the intrinsic carrier concentration, etc., etc. So that change from material to material. And so, as an example, I've told you like how it changes. So if you make a germanium photo transistor, so somebody is trying to join. Let me just. Yes. So what I was saying is that suppose now you make a photodiode, photo detector using germanium, then this level of current will be higher. So whatever it is, so see, you can see it is in some 10 microamperes maybe. But for silicon, it will be lesser if you use a silicon photo detector. So it completely depends. So this is basically this level, the dark current will be basically the reverse saturation current which you get, which is actually I naught, and it changes from material to material and has these values for silicon and germanium.
Okay, sir.
Is it clear?
Yes, sir. Yes, sir.
Okay, so what are the applications of photodetectors? So one example is like using it in an alarm system or a motion sensor, you can say. So suppose when there's a light source and you have a photodetector in front of it, and in between, if some obstruction comes, then this light source is stopped, and there is a drop in the current in the detector, and some alarm system can be triggered by the drop in current. So that means this whole setup acts like either you can say a alarm system or as a motion sensor. And similarly, photodiodes can be used in conveyor belts, where you want to count the number of items which are moving on the conveyor belt. So whenever an item comes in between the detector and the light source, the current in the photodetector will drop, and the counter will go up by 1. So the number of times such items will cross the conveyor belt, the counter will keep on counting it. So in this way, you can use a photodiode detector for counting items on a conveyor belt. So these are just some of the use of photodetectors. Okay.
Sir, in nanoparticle level also we will detect now using this detector.
Nanoparticle level you are asking about.
No, sir, just asking, sir.
I don't think you can, I mean, if you want to detect one nanoparticle moving through a detector, then you need to make a light beam very as small as of spot size of nanometers. Okay, so yeah, so why we can use this photodetectors as to detect something like this. So I have shown you 2 examples where you can use photodetectors. So the reason why we can use is because their response is very quick. So when I mean response is quick is that if suppose the object moves in between the light source and the detector, then the current drops. But suppose if it takes a lot of time for the current to drop after there is a drop in the level of light, then what will happen is by the time the next item comes into in the middle of this and blocks this light, by that time the current in the photodiode is still dropping from the previous item which has come. So this photodiodes detectors have to be very fast, means their response time should be instantaneous, means like if the light intensity falls, the current falls immediately. So suppose every 10, you can have some applications like in which every 10 seconds you are getting a light pulse, means your light pulse is coming at an interval of say 10 seconds. So suppose this is your light intensity and how it is changing. So it is going up and going down. And this is happening in say 10 nanoseconds. So this may be the gap between 2 light pulses. And this light is falling on a photodetector, and you want to be able to get a current. So this is light, and you want to be able to get a current which is also showing the same, means whenever light is increasing, the current is increasing, whenever light is falling, the current is going down. So you need to faithfully convert this light pulse into a say current versus time thing. So for that you need the photodetector to respond immediately to this thing, and so at least it should have a response time less than 10 seconds, otherwise 10 nanoseconds. So suppose this is 10 nanoseconds here. Otherwise what will happen is you will not be able to faithfully reproduce this series of light pulses as a pulse in the current. So that is why the photodetectors have to be having a very fast response time. So that is why this is possible, because the response time is very fast and they can respond to few nanoseconds width of light pulses. And how can we actually improve the response time of photodetectors? So actually what happens is when light falls on the, so you know that we have a PN junction, right? So when you have a PN junction, so you have the PN junctions, and then you have the depletion region. So this is the depletion region at the junction of this P and N type. And in this depletion region, you know that there are space charges, but there are no electrons and holes. And in this depletion region, there is an electric field. So the electric field is confined between this boundaries of the depletion region. So there the movement of this electrons, minority electrons and minority holes is taking place because of electric field, which is known as drift. So the drift is the method or the phenomena by which these electrons and holes are moving in this depletion region. Whereas in the neutral P and N type regions, the movement is mainly because of diffusion. So diffusion is, compared to drift, is a slow process. So it takes more time to diffuse than it takes to drift. So drift is a quicker process. So what we need to do then to make photodetectors very response time of photodetectors very quick is that we need to make this width of the depletion region larger, so that the whole light can be absorbed in the depletion region, and this will enable them to be quickly moved to the other side and contribute to the increase in current very quickly. So if the electron hole pairs are generated, all of them are generated in this depletion region, they will be moved away to the other side by drift, and then that is quick. So rather than allowing the light to fall on the P type and the N type regions where the carriers will diffuse and it will take more time, so the response will not be very quick. Our aim should be to see that the whole of light is falling on the depletion region. So we need to make the depletion region large. So most of the light is absorbed in the depletion region, which will enable the electron and holes which are generated to be carried very quickly by drift due to electric field. And then it will be a quick process and the response time will be small. So that is the idea or the principle behind how you can make photodetectors have a very quick response time. So the response time of photodetectors can be improved by increasing the width of the depletion region. Most of the photons will be absorbed in the depletion region and not in the P and N type regions. This will reduce response time because between illumination and increase of current, because the electron and holes in the depletion region are drifting across the junction by electric field, which is a fast process compared to diffusion, which is the main process which is taking place in the N and P type regions. Okay, so that was the main.
Sir, here we are using drift. Due to drift, this will be increasing. Sir, in case depletion layer will be increasing, inside the electric field will be decreasing, na? Due to decreasing of electric field, drift also will be decreasing.
The electric field does not decrease. The electric field is constant in this region. So if you draw the potential.
So in case depletion layer will be increased, electric field will be constant always.
So the magnitude of the electric field, I'm not saying like if you have a small depletion region, what is the electric field? If you have a wide depletion region, what is the electric field? Whatever the electric field, doesn't matter. What I'm saying is that there is always an electric field in the depletion region. And if you make the depletion region large, then what will happen? Most of the electron hole pairs will be generated in depletion region. Now, what is the benefit of that? Because in depletion region, they are moving by drift, which is a fast process compared to diffusion, which will take place if you generate electron and hole pairs in the P and N type regions. So compared to that, this, if you generate all of them in the depletion region, it will be a faster process, and the photodiode will have a smaller response time. So that is the idea what I'm trying to stress here. That is always the aim should be to maximize the generation of electron hole pairs in the depletion region, because there they can move faster rather than in the P and N type regions, which are neutral.
Yes,
And the reason,
yes, sir, I got it, but I have a little bit confusion. Here, depletion layer will be higher, electric field will be same, but in case light will be fallen, more electron hole will be generated. If they want to move towards the n side and p side, it wants to some electric field. That electric field is sufficient to move these electrons and the hole due to the respective side. I mean, it will be more now. It will be more means they want to more force to move that side.
So if you remember what I told you in PN junction, so when I told you about PN junction, the electric field is only in this region. So this is the electric field here.
Yes, sir. Yes, sir. Yes, sir. Only inside.
Only inside here. So that electric field actually is facilitating the movement of minority carriers, not the majority carriers. So electrons in the p-type region and holes in the n-type region, the electric field is acting in such a direction that it helps them to move from, say, of electrons to move from p side to n side, and of holes to move from n side to p side. Okay. So
Yes,
that is
sir.
exactly what we want here. The minority carriers are generated by light, and we want them to go, for example, the electrons from p side, we want them to go to the n side, and we want the holes in the n side to go to the p side. And that is facilitated by the electric field. So this electric field by itself is letting them go in the direction which we also want for the reverse current to flow. Yeah, so so still do you have doubt in this?
Sir, what I am asking, I am understand concept, sir, but I am asking more and more electrons will be generated.
So that has nothing to do with the electric field. The electric field is not changed by the generation of electrons and holes. Okay. Yeah. So what is the question? If more and more electrons and holes are generated, then what will happen?
Yes, sir. More and more electrons will be generated. They want to flow to one side to another side.
So the electric field, if I'm correct, it enables electrons to go from this side to this side. So the electric field is in this side. Yeah. So electrons here can go in this direction because of the force, and the electric field is in the opposite direction. So where is the problem? And holes in the n side will experience a force in this side, so they will come to this side, which is all right. So the current is from n side to p side, is a reverse current. So where is the issue here?
The issue means so many it will be generated. They want to so much force. In case depletion rail will be.
So what happens?
This electric field.
No, the depletion region is not being affected by this generation of electron and hole pairs. So that is a constant thing there.
No, sir. I am asking moving drift, sir. Moving. I am asking drift.
So drift. Yeah, drift is because of electric field, not the other way around.
Yes, sir. Due to electric field, this will be drift. In case depletion layer will be increasing, that drift also drift will be decreasing. I am thinking, but I don't know.
No, it will not happen like that.
Okay, sir. Okay.
You are thinking completely. Depletion will increase. I'm saying that the depletion region should be wide enough, so there will be an electric field over the whole region. So that has nothing to. I mean, if the depletion region increases, drift will decrease. I don't see where you are getting that idea from. Okay, so
Is there any limit to the depletion layer, sir, in the material?
Of course, it has to be between the boundaries of your material. Whatever your PN junction is dimension, it cannot be more than that, and it will be always less than that. Okay, so yeah, so now how does the band gap of the material which has been used to make this photodiode or photo detector, how does this affect the wavelength of light which this photodetector is sensing? So for example, we can make a photodetector from a germanium or a silicon material, and then how will that affect the kind of light which we are detecting? So what do you think is going to happen if you use a germanium to make these PN junction, or if you use silicon to make this PN junction, what will be the difference and why?
Sir, can once again ask question, sir?
So if you use germanium and silicon, two separate materials, once you use germanium and once you use silicon for a photodetector, how is it going to affect the working of the photodetector? What changes you will see?
In case we are using in germanium, that it will be giving more power. I mean more current.
Photo detector has less response time.
How do you know that? Response time. Well, more current because reverse saturation current for germanium is higher. That is fine. But actually what I'm trying to say is that what is the band gap of germanium? Do you know?
So 1.1.
No, that is for silicon.
Has,
I don't know. I think it's 0.33 electron volt, but just check it because I wrote this from my memory. I'm not sure if it is correct or not.
so then
But suppose it is, sorry?
0.67.
Germanium is 0.33.
Okay, maybe 0.6. So maybe I'm wrong. You're right. Sure. Anyway, that you can find out. It is not a big issue. So whatever is that. So but the fact is that it is less than the of silicon. So silicon is 1.1 electron volt. Now, so it can only absorb photons which have energy greater than the band gap. So germanium will absorb photons with energy greater than say 0.33 electron volt, and silicon will absorb say greater than 1.1 electron volt. So that means, as you know, the wavelength is inversely related to the energy of photons. So for longer wavelengths, means like infrared or near infrared regions, both will actually detect because silicon band gap is 1.1 electron volts, so it can detect only wavelengths which are shorter than 1130 nanometers. So it cannot detect any wavelength which is larger than this 1130 nanometer, because then its energy will be less than its band gap. But basically it detects photons near this wavelength. And similarly for germanium, it will, if you use 0.33 as the value of the band gap, you get 3700 nanometers as your wavelength. So it can detect wavelengths which are smaller than this. So that means you can use the germanium photodiode for more in the infrared region compared to the silicon. Although both are falling in the infrared region, but this is in the even deep infrared region, which if you will see, it is actually known as the near infrared region. So this is the near infrared region, and below 1130, it is actually the infrared region. So germanium photodiodes, photodetectors, you can use further into the infrared spectrum as compared to silicon. So that is one difference you'll see. So that is what I wanted to tell, that depending upon your band gap of the material which you are using, sensitive, that also changes. So that is what is basically I was trying to illustrate here. So the material, so the photodiode, to what kind of wavelengths it will be sensitive to, that it depends upon this material, basically its band gap. Okay, so any questions here? Okay, so no questions, then I will proceed to the next part. Okay, so next we come to light emitting diodes. So let me just see then, how do you get light in a light emitting diode? So what is the mechanism behind this? How do you think you are actually getting the light is being generated? Yeah, nobody has any idea?
So due to recombination of electron hole pair,
Okay, so can you
Sir, radiative recombination.
tell a little bit more about that?
Sir, whenever light is fall into any material, in electron will be excited to valence band to conduction band. Due to that electron, that will be
Yeah, but right now we are talking about light generation. You are saying about light will be incident on that. So we are talking about the reverse thing. Okay, let me just let someone who was
that-
speaking before you, let him speak.
Sir, okay.
Yeah, so continue what you were saying.
Sir, that electrons will be going to downside. In that time, that will be emit some energy.
No, I was asking the other student. Was
DNB,
what is his name?
Brahmana.
sir,
Yeah.
when the diode is in forward bias,
Mm-hmm.
the barrier will vanish.
Will vanish.
Yes.
Okay.
So, in the depletion region, electron or holes will recombine.
Mm-hmm.
Then due to
Okay.
the recombination of electron and hole pair,
Mm-hmm.
uh, I think
Light will be generated.
light will be generated, but I don't know which wavelength will generate. I forget, sir.
Okay, so tell me, when you forward bias, how is the flow of electrons and holes taking place in the PN junction? Like in where to where the holes are going and from where
Due
to
to
where the
majority
electrons are
carrier,
going?
sir.
Yeah, so just explain in a little bit more detail. So
Sir, electrons
suppose
from
someone doesn't remember right now, so can you just explain more detail?
electrons
No,
from
your voice I could not hear. Can you repeat?
okay, sir. Electrons from inside
Mm-hmm.
will go towards
P side.
yes,
Okay, and holes
and
from P
holes
side to N side.
yes, sir.
So the electrons from N side, they are the majority carriers in that N side, right?
Yes, sir.
And similarly, holes on the P side, they are majority carriers. And so the majority carriers are being pushed by the forward bias to the other side, right? That
Yes, sir. Yes.
is what you're saying. Okay, so when this majority carriers electrons in the N side reach in the P side, what do they become immediately?
Sorry, sir. Can you repeat?
So as soon as this majority electrons from the N side reach the P side, what do they become? They become minority carriers, right?
Yes.
Because it's the P side. So basically what is happening, you are injecting
They will
minority carriers into the other side. Like when you are forcing the electrons from N to P, you are injecting minority electrons into the P
Sir, can
side.
you
Similarly, when you are
draw
forcing
here what
holes.
DNB tell? Sir, can you draw like a picture?
Yeah, what will I draw? The hole and electron thing?
I mean, what he is explaining something.
Okay. So this is your PN junction, okay? So this is the depletion region. This is the junction. This is P, this is N, okay? So in the depletion region, so in the P side region, holes are the majority carriers. And the N side, it is the electrons which are the majority carriers. So when you forward bias this, these holes, they are pushed to this N side, and these electrons are pushed to this P side. So these are the majority carriers in the N side electrons and the holes in the P side. But what I was saying is immediately as soon as this electron reaches this P side, it becomes a minority carrier by definition, because this is the P side. So there are more holes than electrons. So this electron has now become a minority carrier. Similarly, the hole which has been injected from the P side to the N side, this hole, it will become a minority carrier, because this is by definition the N side, where there are more electrons than holes. So what we are doing is basically, when we forward bias this PN junction, we are injecting minority carriers. So we are injecting electrons into this P side, and we are injecting holes into this N side. So that is what I was saying actually.
Sir, then why normal lights is not emitting light?
Normal diodes are not emitting light. That is a very good question. Actually, that is what was in my next page. So we'll come to that. But okay, so what is your name?
Brahmanand.
Brahmanand. So what Brahmanand just told a little bit ago was that he said that this electrons and holes which come into this depletion region, they recombine and then they give light. So that is exactly what is happening in light emitting diode. When this diode is forward biased, holes and electrons are pushed into the depletion region and there, or in the, so when this, so what will happen is, for example, this minority electron in the p side which has been injected, it will recombine with the holes, and the concentration of this injected electrons will go down as you go far into the p side. Similarly, a hole which has been injected in the n side, the concentration will fall down as you go towards the end of the n side. So that is how this concentrations of p. So this is basically what I have drawn is number of electrons n, and this what I've drawn is number of holes p, and this is distance. So this is distance on the x-axis, distance from the depletion region. So as you go away from the depletion region, the concentration of this minority injected carriers is going down. That is what I've tried to show here. And why they go down? Because they recombine. So they recombine, this injected electron, it recombines with so many number of holes that it will recombine. Similarly, this injected hole which will recombine with so many number of electrons which are there. And so the concentration also goes down. So because of this recombination, so you know when electron and holes are generated, you need energy, either thermal energy or optical energy from photons. Similarly, when you combine this electron and hole together, which is known as recombine, you are supposed to get back that energy. So when you have this kind of band structure, this is the conduction band, this is the valence band. To create a vacancy here and to create an electron state here, you need this much value of energy. Now, if this electron goes and fills this vacancy, then you emit the same amount of energy back. So you generate a light photon. So exactly that is what is happening here in light emitting diode, and that is what is going to give you light. So when you forward bias the PN junction, you get light. So that is the basic functioning or principle of light emitting diode, and which brings us to the next question of Brahmanand, which we'll just now deal in the next page.
Sir, another question also.
Okay.
What kind of light means? What is the wavelength of light? How the wavelength will vary?
Yeah. So that is the same question which you have just asked. So we'll answer both. I mean, it's the same question actually. Okay. So in a forward bias diode, the
Hello,
majority
sir.
carriers
Sir, this band diagram will be appear inside the depletion layer or entire whole material, sir?
Band diagram is a material property. So it is the property of the material which has been used to make this diode. So even in the doped regions, p-type, n-type, the band structure actually doesn't change much. But yeah, you get impurity levels in this band gap. So there are some levels in the band gap. Those levels will depend upon your p and n-type regions. Otherwise, the band structure will more or less remain the same over this whole p-n junction, because it is the property of silicon or say germanium. So the band gap will, for example, not change whether you are here or you are this side.
Okay, sir.
Yeah. So as I said, these holes and electron recombine and in the process release energy which is equal to the band gap. So whatever the gap, that much energy will be released, and from that you can calculate the frequency of light, or you can use hc by lambda to get the wavelength of light. is whether the band gap is a direct band gap or it is an indirect band gap. If it is a direct band gap, only then you get lot of light emission, means majority of this energy will be liberated as photons. So most of the electron hole pairs which will be recombined, most of them will liberate as light energy. But if your band gap is not direct, it's an indirect band gap, then in that case, there's a very small emission of light, a very feeble light emission. So you won't get that good light emitting property. So you will not be able to make a LED out of it. So you need direct band gap semiconductors to make LED. So this PN junction you can make with any material, any semiconductor, silicon, germanium, gallium arsenide, gallium phosphide, etc. But you will get a good light emission. Majority of the recombining electron holes pairs will give you light if their band structure has a direct band gap. If it is an indirect band gap, then they won't give light. So that answers the first question of Brahmanand. That is, what will decide why some PN junctions don't emit light? That was the first question, right?
Sir, can you distinguish distinguish between direct and indirect band gaps? Sir?
Yes. I have not told yet what is the distinction.
Okay,
but
okay.
Is it clear that direct, if it is then there is light emission in large numbers, which is required for LED. Right, Brahmanand, is it clear to you?
Yes, sir.
Okay, so what is the direct band gap and what is the indirect band gap? So this picture which we should draw of the band structure is a very simplified band structure. So this is the wave vector and this is the energy scale. But actually it need not be. So this is the bottom of the conduction band. This is the top of the valence band. But it need not be so simple a band structure. There can be more states. So it can be like, there can be another band like this. There can be another band like this. Even in this case, this is not a conduction band because there is this blue band is lower than the orange band. So always the lowest energy level in the conduction levels is known as the conduction band. And similarly, which is the highest level in the valence states, that is the top of the valence band. So again, this blue is higher than this orange, so nothing will change. This will still be conduction band bottom, and this will still be valence band top. But we can have, sometimes it can be possible that you have say something like this. Okay, and and then you have something like this. So this is the valence band and this is another conduction band which I've drawn. Now you can see the band gap is the gap between your bottom of conduction band and top of valence band. So which is the bottom of the conduction band now? Is it the orange, blue, or the green curve? And where? Which is the lowest energy level of among the conduction bands?
Sir, this green is lowest, but we will
Yes.
consider.
Yes, so we will. This is the lowest energy, this point. So it corresponds to this value. That is the lowest. So this is the bottom of conduction band now, bottom of CV. Now the problem is the top of valence band remains the same. So it is still here because the green and blue are coinciding. But now you see that the band gap is not direct because the band gap is between this point in K. So now notice that these are with respect to K. So K is 0 here. This is some non-zero value of K. So what is happening is your bottom of conduction band is at a different value of K, which is this. And the top of valence band is at this value of K, which is 0. So this is the example. This blue was the example of direct band gap. And this green current one is an example of indirect band gap. So if you want to show in a simple way again, this is a direct band gap. And This is a example of indirect band gap.
Sir, in direct band gap, photon is emitted and indirect phonon is emitted, na?
Yeah, so what happens is basically what this means is this electron has a different momentum because k is a momentum wave vector. So you multiply by h bar, you get h bar k, that is a momentum, p equal to h bar k. So what it means is this electron has a different momentum and this hole has zero momentum. So when you want to combine a hole with zero momentum with an electron with a non-zero momentum, that requires that the total elastic collision requires momentum to be conserved. So you need another
Sir, can you once
phonon
again
there.
tell me, sir, your voice is not properly coming.
Yes, so what I'm saying is that, as he said just now, that phonon is required in this indirect band gap transition. The reason why it is required is that you can see the electron has some wave vector here, non-zero k. Non-zero k means your momentum is non-zero. H bar k is the momentum. While here your valence band has zero momentum. So its momentum is k is zero, so h bar k is also zero. All right. So that means you are trying to recombine a momentum electron which has some momentum with a hole which has zero momentum. So you need to also, you know, that when they recombine, they are annihilated. So where does the extra momentum go? So that extra momentum has to be given to something to conserve the momentum. As you know, elastic collision everywhere, momentum is conserved. So to conserve momentum, you need the extra momentum to be given to something. So that extra momentum is phonon, which is basically lattice vibration. So you, when this happens, you also need a collision with a ion. So electron, hole, and ion should collide together to create this emission of light. Only then this light will be emitted. So that phonon extra is required to balance this momentum. Whereas in the direct band gap, both have a zero momentum. So there is no need of any extra phonon to balance the momentum. So in the indirect transition, you also require another phonon to carry away the non-zero momentum which was there in the electron. So that is one of the reasons why. So phonon, if you make a phonon, what is happening is basically you are vibrating the lattice, which is heat energy. So vibration of ions is nothing but heat energy, right? So that is what we call as phonons. So that means that is why we are saying that when there is indirect band gap, there is more probability that instead of light, heat energy will be evolved. So that is why silicon and germanium are indirect band gap semiconductors, so that generally in those kind of diodes, you will not see light emission because very few of those transitions or recombinations will give you light. So you need some direct band gap. So for example, gallium arsenide is a direct band gap semiconductor. So when they will combine, you will get, most of them will give you light. But again, its band gap is some 1.35 electron volts. I think it's in the next page. Yeah, so this is the 1.43. So its lambda is coming to 869, again, which is not in the visible region. So it is again in the infrared region. So we'll see that which materials will give you LEDs in the visible region. So what is the use of LEDs which are giving light in the infrared region? What do you think is the use of them?
So we can thermogun like.
And what you're saying?
Sir, infrared light has many applications.
Yeah, so example. Okay, so I've written down some applications. So for example, gallium arsenide is a direct band gap semiconductor. Its band gap is small, so it emits light in the infrared region. It is suitable for applications in security applications, like again, motion sensors to detect somebody is moving or not, industrial processing like conveyor belts. So those sources of light can be infrared. They don't need to be just optical visible light. Then optical couplers.
we can determine the temperature. Means we can sense the temperature.
Yeah, but that requires infrared light, but here you are generating the infrared light, right? So you need a photo detector in that case. You don't need a LED. So optical couplers, like you want to connect two optically two devices, means you have a photo detector and you have a LED, and LED is emitting infrared light and photo detector is detecting infrared light. So you are making an optical coupler. So information is going from LED to photo detector as a light. So there's an optical couplers and safety devices like door sensors, which will automatically stop, which have LEDs, which are emitting infrared light. And of course, like remotes, which you have in every house has remotes for ACs or for TVs. So all of them emit infrared light. So they have LED, which is emitting in the infrared region. So those are the use of infrared. So even gallium arsenide, which is having a low band gap, 1.45, it has use as infrared LEDs. Okay, and so this is just a picture of an LED, and you can see that a lot of gap has been left in the metal contact so as to allow light to be passed away. Whatever light is generated so that it can leave. Okay, so I think I will stop here today and we'll continue from here in the next class. All right?
Sir, sir, in indirect band gap only we will give to vibration. Due to vibration, that electron will be movement to that.
No, in indirect band gap, along with electron and hole combination, you also need a third person, and that is the phonon, because that extra momentum has to be given to somebody. Because after combination, there is no electron and hole. So who has the momentum? Somebody has to have the momentum. So that is the phonon. So you need a 3-particle collision in the indirect band gap thing. And so the phonon will also carry some energy, right? Only momentum it has no energy is not possible. So it will carry some energy also. So basically those reasons is why if you have an indirect band gap, you will not get emission of light. It will mostly be heat energy which is generated.
I mean, 1% also we didn't get.
No, of course, in 100 photons, maybe 1 or 2 will emit light. But for that LED purpose, it is not sufficient.
So these phonons we will give to that
Phonons are always there. Phonons are nothing but your lattice ions which are moving. So it is basically electron and hole is colliding with the ion in the lattice.
In
That is a
normal
phonon.
in normal direct band gap, no phonons is there, na?
Phonons are there. Phonons are there because even in the direct band gap semiconductor, there are ions, and the ions are vibrating, but that they are not involved in this optical transition or electron hole recombination. There is no need for a phonon to also interact with the electron and hole. That is the difference.
Okay, sir. Sir, is gallium arsenide we are giving direct band gap. This
It has
silicon,
this kind of structure, band structure.
in silicon also like this.
It has this kind of structure, indirect band gap.
Oh, indirect. Okay,
Sir,
Silicon and germanium.
So
Sorry?
sir, in direct band gap, there is phonon, but no momentum is transferred to phonon. Na?
Yeah. So it is not required in this electron and hole recombination thing. There is no need for that. There are phonons, but they're not interacting with the electron and hole recombination part. But there is a, in principle, requirement in the indirect case. Without it, it will not work. That is the difference.
sir, we don't prepare to silicon and germanium LEDs.
Yeah, so generally you'll not prepare because their yield will be very small and you will need a lot of recombination to get
Only
sufficient light.
gallium arsenide. Is there any?
No, there is a whole family of compounds. So gallium arsenide, gallium phosphide, and then you can combine 3 gallium arsenide phosphide. Then you can combine
Hello, sir. Hello, sir.
Thiru.
BNB, sir voice is audible to you.
No, no.
Okay, okay, okay. I think sir is left. Okay. Oh, sir is here. Hello, sir.